So for starters, we're going to go over the electrical system of the heart and how the normal impulses should travel through the heart. So for starters, the very, very first impulse, everybody should know, comes from somewhere up and around here. Okay, and that's coming from the sinoatrial node. Sinoatrial node. And this is coming from a region called the sinus venerum. It's just next to the where the SVC drops off into the right atrium. Thus, sinus venerum, sinoatrial node. This is the chief pacemaker in your heart. So I'll write this. Chief pacemaker. And it's what should generally be starting all of the conduction system moving down. So this is the very, very first one, and it determines the overall rate of the heart, unless something is going out of whack. From there, okay, the next stop it's going to go, it does a couple little weird things here. So the next stop we should know is called the atrioventricular node. Okay, and we're going to draw that just up over here. Atrioventricular node, or an AV node. I'll put a SA here and an AV here. So AV node is kind of like our speed bump. Okay, as the signal goes from the SA node to the AV node, it should go to the AV node and just hangs out a little bit. We have this thing called atrial kick. So we want those top atria up here, right, to dump their blood down into the ventricles. Okay. But the thing is, if they were to send this signal along, the ventricles are just going to start contracting. So as soon as this blood is starting to hit this valve and get through here, the ventricles are just going to be closing it off and sending it. So what we want to happen is the SA node for these atria to contract and send their blood down in here. And we want it to hang out for a second so these ventricles can actually fill with blood before they contract, send this signal to the ventricles and so on, and then push that blood out. So how it gets here, this is one of those things that usually gets missed, can be a little wonky. Okay, so like I said, the SA node can be kind of weird when it's going from the SA node to the AV node. So whenever one of these cardiac cells gets a signal, they don't care where the signal is coming from. They just care that they're getting a signal. It's if we had a little line up here of a bunch of very happy little cardiac cells, right? If this guy decides, hey, it's time to party, right? He throws his hands up. This guy here doesn't know or care why he's doing it. He just cares that this guy, seems like he's having a good time. So he's going to throw his hands up and party, right? And that's going to keep going down the line. So when the SA node kicks off here, it sends this signal in all directions. So all these cells going out in this kind of circle, right, they all start going off. Now the issue with this arises from when we need this signal to kind of travel directly to the AV node. If we were to do this, right, it's going to go here, 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 and then eventually gets to the AV node. That isn't very conducive for, conduction. So our heart has a couple of super highways, okay? So there's generally 3 that are going to go like this, and they go from the SA node to the AV node. We also have one more that's going to come up over here to our left atrium. So what winds up happening is that the right atrium here is going to go off, depolarizes, so these heart cells are going off. The right atrium contracts from this signal, and simultaneously it sends this signal very quickly over to here, so that this way the left atrium can start that as well, right? Otherwise we have to go here, 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 travel the whole way up and across before the left atrium contracts. Regardless, there's a little bit of a gap here, so the right atrium contracts very closely with the left atrium, but still slightly before. The important thing is that these superhighways allow this to happen pretty quick. So even though this signal would take a bit to travel to the AV node, with these superhighways that are going to the AV node, it can get there a bit more quickly and be able to pass this on. Okay, that's an important concept to remember later. We'll come back to it, but if you understand that part, you're going to understand some pretty cool stuff with the 12th lead. Now from the AV node, okay, it's hung on to that signal for a little bit, and now it decides, okay, we can pass this on. Okay. So what's going to happen is it's going to cross the interventricular septum. So that's this area in between your left and right ventricles, right? So it's going to cross this, and it's going to go to a place called the bundle of His. Bundle of His. And what that's going to do is it's going to spread this signal to the two bundle branches. So each of these ventricles we want contracting at the same time, right? We want this to come in and this to come in, similar to how we have this up here to try to help the left atria and right atria to contract relatively at the same time. We want the ventricles to contract at the same time. Otherwise, if the right ventricle contracted too early, that same force can be exerted onto the left ventricle, or the signal could wrap around and cause other issues. So, the heart being as smart as it is broken up two bundle branches, so these two superhighways again that are going to wrap through for each ventricle. Okay. So we went from the SA node to the AV node. That goes to the bundle of His, which breaks that up into our two bundle branches. That's going to be a left bundle branch and a right bundle branch. And that's going to lift this on up through the ventricles. And then we get to our Purkinje fibers. Okay, and what those guys are these little fibers that go up through the ventricle this way. So this way, in everything going correctly, okay, the ventricles are going to contract from the septum in like this. So this will start it. And then just like if you were squeezing a balloon, it's going to squeeze from the bottom and work its way up. Okay, so we start our contraction from the septum to the apex and then up. So we squeeze the blood up and out and then through our aorta or our pulmonary artery. So each part of this is what we're going to wind up drawing out whenever we get to the actual 12 lead interpretation part. Okay, so again, so long as you understand this, and if you need to come back and rewatch this or go find Khan Academy has great videos on. From there, the next part is understanding what the EKG even is. And if you ask the electrophysiologist or cardiologist in the hospital, this part can get kind of wonky if you start getting too in-depth into it. So we're going to look at this at kind of a basic layer. Okay, if you want to look at how the EKG literally works, quite frankly, it's magic. It just appears stuff onto the screen in a way that, quite frankly, does not make sense. Uh, it's one of those things. If you understand the basic part of it, it makes sense. If you try to understand the more in-depths of it, that's where it starts to become like quantum physics level of confusery, at least to me. Uh, but we're just going to touch on the easy part here. So each EKG is going to be formed of two electrodes. Okay, so we're going to have two electrodes. And just like anything in electricity, we're going to have a negative side and a positive side. So what they're going to do is you place these two things, these two electrodes, on a person, okay? And they're going to pick up the change of electrical current in between them, okay? And what they're really picking up on is really just kind of a linear point A to point B. So whenever we have our line of cells, let's say we take those cardiac cells again, they're all going to be nice and happy in a straight line here. Put some little friendly faces on them. What's going to happen is the plus and minus, these two electrodes, they pick up on the wave of depolarization or that movement of depolarization. So when these guys wave their arms up and they're like, yay, it's time to party, right? and they go to the next guy and the next guy, so they're moving this way in this case. Okay, so going this guy here to the next one to the next one and moving down, this creates a wave of depolarization as these cells depolarize, and depending on the direction that this is moving is where we get our drawing onto the EKG. So if we're moving, in this case, from the negative towards the positive, okay, so if this wave of depolarization is moving towards the positive, we're going to have an upwards deflection, right? So if we were to draw this out, and these guys were just to depolarize real quick, going in that way, we get our positive deflection. Now let's say it went the other way, right? Let's say this guy had his little happy face drawn back on him, and what if this guy started it? He said it's party time over here, and then this guy, and it moved this way. If that's the case, we're moving away from the positive. That same drawing that we had before, this time, is going to be a negative deflection. Okay, so towards the positive gets us a positive deflection. Away from the positive gets us a negative deflection. Now, where this gets a bit more wonky, and the important concept here is that this only works in a 2D or a linear fashion. Okay. So let's say we take those same cells, but we're going to stack them up, because obviously the heart cells are not just a straight line of cells. They go kind of in a mash, right? So we'll make a grid of all of our happy little cells here. And then we're going to draw our negative again up over here and a positive again. So if our first guy, let's say this guy here, he decides he wants to go off, he's going to send the signal in all directions, right? But let's say it's going this way. If it's going that way, because this is a straight line, we're going A to B to C, right, along this line. So from the negative to the positive, since it's going towards the positive, it's going to see a positive deflection. Now, let's say instead, he's sending that signal upwards, right? He's sending it to that guy. If he's going here to here, on this x-plane, right, this just between here and here, for the sake of this, there's no movement. Okay, there's no left or right movement. It's going up and down. So in this case, the signal that's going to come through it is nothing, because there's no left or right movement. If it were to go, say, downwards, right, it would be the same thing. Because there's no left to right movement along this plane here, we would still have a negative, or no amplitude or anything whatsoever. There would be no signal. But obviously that's not exactly what happens. So the way we change this up is we set up another electrode, right? Because these have to be in pairs. We can set up another one here. So this one is looking like this. So that's become our Y, and this is our X. Just like looking at a grid in mathematics, right? So now, if we have this guy, and he's going left to right, for this first one here, up along the top, because it's moving towards the X, it gets a positive deflection. But because it's going this way, for this one here, right, there's no change in that one. It's not going towards a positive. So this one sees nothing. Similarly, if we were to now start here and we're going to move upwards, there's no left to right. So this one sees nothing along the top because there's no left to right movement. But there is an up and down movement. In this case, since it's moving up, if we were to draw this here, it's moving towards the negative, at which point we'd have a negative deflection. Now, whenever these are picked up on the EKG, they're being picked up as a vector. Okay. So if we were to say that this guy went off with a force of 2, okay, just for the sake of explaining this part because, again, when you get more in depth, it can make things kind of confusing. Let's say he had a force of 2 going this way. That's going to make a deflection, let's say, this big. Okay. So if we were to put our little markers here on our EKG, this would be like a 1, this would be a 2 here. Right, so that's a force of 2. But again, there's no change here, so even though there's a force of 2, for this one, there's nothing. And we could do the same thing to the other way if we were to go back down. This one would now have the force of 2 because we're going towards the positive. And this one has a force of 0, so there's no change there. Now, if this goes at a 45-degree angle, right, if we're to split the difference between these two, right, so instead of 2, right, going this way, that big force, or 2 going this way, we now have half the force going down and half the force going up. So instead of there being a force of 2, there's now a force of 1 on this one. And where this one had those two little hashes, this one is also getting a force of 1. So you see, because it's gone at that 45, we've halved that electrical signal here on both of these. But now using this, if we were to look at this, we can see it has a positive deflection. We know that this signal is going towards the positive this way. And we know with this one, the signal is going towards the positive this way. And this here is the basis to the next concept, which is the electrical axis. The electrical axis is just a form of exactly what we just did, placed basically on a grid. Okay, so if we were to take our same grid, and what we're going to do is we're going to draw a circle here, or the best circle I can give you. Okay, and we're going to have the first lead. We're going to call it lead A, and then we're going to have lead B. All right. So if we were to look at lead A, and let's also figure our starting point is always going to be here. Okay. If lead A comes out as a read, like so, and lead B comes out like so. Okay. And lead B being this one we had here before, so this is B, and then we put this here is A. Okay. So with lead A, we see a positive deflection. So we know that this is going this way somewhere. So we don't know exactly where in this circle this is, but we do know it's got to be somewhere in here because it has to be heading to the right of the circle. Okay. Now we take lead B and we see it's negative. Okay. So that means it's heading up. So we can take this and we can kind of just color this all in. But we see where this crosses over here, right, is somewhere in here. Now we could use some math to really figure out exactly where this is, but for all intents and purposes, we've triangulated to know that this signal is going generally in this direction. Okay? So we could do the same thing and just keep applying this. So let's say lead A now looks like this. Okay? And lead B, let's say it's also negative. We'll do the same thing and draw it out. So lead A, since it's a negative deflection, signal is heading away from its positive. So we split this circle in half. The signal is coming from somewhere this way, right? Or it's going somewhere in this direction. We do the same thing for B here. We know it's going towards the negative, so in this case it's heading up. So it's in the top half here. And where these cross over winds up being this quadrant. So that means that this signal, in this case, is heading somewhere up in this direction. So this, again, important concept. We'll go over a bit more in depth. If you understand this, you understand already how to read an EKG. And maybe if you've done some kind of like EKG or rhythm interpretation, certain things are probably starting to click as to why when you look at something that says lead 1, lead 2, lead 3, and why those look different even though we're looking at the same heart.